Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Hello, welcome to the SEI Podcast Series. My name is Matthew Bakovic. I'm the Technical Director for Cyber Risk and Resilience in the SEI CERT Division. Today, we're here to talk about SBOMs, Software Bills of Material, a critical tool in understanding supply chain risk and ensuring that we produce quality software. A key challenge is ensuring that no matter what system or tools we use, comparable SBOMs are produced. I'm joined today by Dr. Jessie Jamieson, a cybersecurity engineer in the SEI CERT Division. Welcome, Jessie.
Thanks, Matt. I'm really happy to be here.
So, Jessie, for folks that maybe aren't as familiar with you and your body of work, let's start with you telling us a little bit about yourself.
Yeah, sure. Thank you for the welcome and for the warm introduction. As you said, I have a PhD in mathematics, actually, and I love using math to solve all kinds of difficult problems. So something that you may not actually know about me is I'm also published in 2 medical journals using mathematics to help solve medical problems. And I've had internships at Oak Ridge National Laboratory and at NASA Goddard, 2 awesome places to work. And at Oak Ridge National Lab, actually, that's where I was first introduced to cybersecurity. Got a taste for it there working with their SOC, which was an awesome experience. And after that first taste, I said, yeah, this is great. I love using math to solve this kind of difficult problem. And cybersecurity is a field that really touches everyone. So everyone can see themselves affected by cybersecurity technology these days. And if there's any chance I can use use math to help solve these difficult problems and make the world a safer place, I'm all about it. So I've touched a lot of different things. I have a lot of different interests. I follow Formula One very religiously, and I love cars. So I've come up to the Pittsburgh Grand Prix a couple of times. So yeah, I'm just very interested in a lot of different things and topics. But I was very interested in helping do some research here on the problem of SBOMs.
Well, excellent. So, Jessie, thank you for providing your background and a little bit of a biography. One of the things you said I think is so important, which is using interdisciplinary approaches to solve problems. We're so glad you joined us here at the SEI, where you're applying your enormous skills in mathematics and other techniques. For instance, I know that you have a specialization in function analysis and PDE theory. When you were earning your doctoral degree at the University of Nebraska, these are things that you learned, applied, and then it sounds like found outlets for not only in cybersecurity but also in healthcare, which is great to hear.
Yeah, actually, the PhD was a really interesting journey because studying PDEs and functional analysis was actually not my original goal. In undergrad, I studied graph theory and combinatorics, and I love the application of mathematics to network science. And when I got to grad school, I changed fields and went in a slightly different direction, which was quite a balance because when I was doing my internships, I applied different kinds of math than what I was actually studying my PhD. So although my PhD is actually in the theory of beams and plates and bridges and things, I studied all kinds of mathematics and bringing that even within mathematics, there's an interdisciplinary kind of approach there where you can apply graph theory, or you can apply network science, or even some numerical analysis and mathematical modeling. There's all kinds of things we can apply to some of these problems. So that's one of the reasons why I love math so much is there's all kinds of different fields within a field almost. And you kind of draw from all of it in order to really chip away at some of these problems. So yeah,
well, excellent. So I know we care deeply about making the world a safer and better place. And one of the ways that we're looking to do that is by advancing the state of the practice and state of the art of software bills of material. But maybe let's start at the very beginning. For members of the audience that may be less familiar with the concept, can you maybe explain software bills of materials and what they're intended to do?
Sure. Yeah, that's a great way to start. So I'm sure most people in the audience are familiar with the concept of a nutritional label or of a shipping manifest. If you purchase something from the internet, you may get a label that tells you exactly what's in your package. Now, wouldn't it be great if we had that for software too? That's really one of the goals. When we ship a package of software or a software or a piece of software and you're putting that in your environment, you should be confident in knowing what is exactly in that package and what you are actually incorporating into your environment. That gives you a better idea of risk, right? So Ideally, we should be able to go down a list and see a full list of everything that's coming with that software package. And our analysis and the work that we've done has shown that there's a little bit of trouble there, and we're going to get into that. But really, if you think about SBOMs as almost an ingredients list, that's one way that I usually think about these tools and these artifacts. So that's basically a very brief, explained like I'm 5 version of what an SBOM is.
That was great. So an SBOM then, as you mentioned, is a list of ingredients, or maybe a little more aspirational, it's actually nutritional information. So it's not just the contents of something, but also the implications of those components, right? So I can see where that's immensely useful in having traceability in your software, but also then when you're presented with a specific threat scenario, it helps you then make risk decisions. So I know we'll talk more about that concept broadly, but I wanted to ask more specifically about a recent effort. So in 2024, you were an integral part of an SBOM harmonization plug fest. Could you explain and maybe decode that name for our audience?
Sure. Yeah. So the plug fest was the brainchild of Dr. Alan Friedman, who had this idea of let's use a bunch of different SBOM tools to produce SBOMs for a set number of software targets. If you standardize the number, or if you standardize the software targets, and when you produce the SBOMs in the course of producing that software, we should be able to then produce a comparable set of SBOMs and go down the line between all of the SBOMs and say, is there agreement across all of the SBOMs for this one particular set of software? We're holding variables constant in this experiment, right? So we're producing the SBOMs at the same life cycle stage of the software, and when we're producing the software, and we're holding the pieces of software constant, so those aren't changing. Actually, for our Plug Fest, what we did was we chose a number of software targets across a myriad of programming languages and software types, and we froze them at certain commits, and then we asked participants of the Plug Fest to use their tools to produce SBOMs for those pieces of software at that snapshot in time. So theoretically, the SBOMs are being produced at the same time for the same targets at the same life cycle stage, and all things should be the same. Spoiler alert, they weren't. Yeah, so it was really awesome, a really great experiment design, and really allowed us to start digging into sources of divergence in SBOMs as they're produced by a number of tools.
Okay, this is really interesting. So the divergence is a problem for a couple of reasons, right? It calls into question the fidelity or the usefulness of the SBOM, right? If we can't trust the output of those systems, then you really can't trust as an input to the risk management that you might need to perform with it.
Absolutely, yeah. That's a huge source of trouble.
So if we want to improve accuracy and veracity of SBOM, how would you suggest that we go about making these improvements? Or maybe, put differently, what are some of the key challenges we found driving this divergence in output?
Sure, yeah. So there were actually quite a number of sources of divergence in the SBOMs that we studied. First of all, there are a particular set of minimum elements that are prescribed to be present in all SBOMs. These include things like the title of the software that the SBOM is produced for, the version of the software, cryptographic hashes, other elements that really allow you to get a very good idea, a precise idea of the software that the SBOM was produced for. We saw actually that even though these minimum elements are very well prescribed, there was a lot of variance even amongst those elements. For instance, the version number for the software packages that the SBOMs were produced for, you could see version 0.2 or spelling out of the word version, or just version 2 or V2, or just within the strings that populated the artifacts that we were given, there was quite a lot of variance. Now, there's also Another source of variance was actually in the dependency structure of SBOMs. Now, as I said before, SBOMs are almost like a nutritional label, or they should be, right? You should be able to see direct links between the nutritional elements of your food and where they are in your food, right? So you have iron and all of these other nutrients. You should, for an SBOM, be able to say, here's my main piece of software, the software package that the SBOM is for, and be able to trace down through your software the individual submodules and packages that the software depends on. And it turns out that what some organizations, not only the producers of SBOMs, but also the consumers of SBOMs consider to be dependencies, results in a lot of deviation across SBOMs that are produced for software. So, for instance, if a software package calls another submodule as it's built, or in a runtime environment, sometimes you would see that submodule listed as a dependency, and sometimes you wouldn't. On the flip side, for different use cases of SBOM, you would see end users looking at the SBOM and say, I expected this package to be listed as a dependency for my use case, whereas for other use cases that the dependency being present or not being present may not have made such a huge difference. So you have on one side the use cases driving the production of these SBOMs and what they're used for, and on the other side, the producers of SBOMs having to almost guess what they think the actual dependency structures or substructure within the artifact should actually be to maximize the usability for the end user. And I touched on use cases. There are a huge number of use cases for SBOM, not only asset management, inventory management. We touched on, I think you mentioned vulnerability management and risk. So depending on what folks are using and end users are using the SBOMs for, they may need different information. Sure. And even that can drive differences across SBOMs, because you may have one producer who is really targeting one sub-audience and another producer targeting another sub-audience and use case. So lots of sources of divergence in these SBOMs that we saw produced, and it came from a number of different sources. Yeah,
so it sounds like fit for purpose is a significant principle here, which is there are different use cases, and it's not as simple as you just turn up the accuracy knob, right?
Right.
So it sounds like that the technical solutions to improve SBOM are probably multifaceted. There's some additional technical complexity that needs to be layered in to have more accurate and useful SBOM.
Yeah, I believe that's true. And I know that recently, at least as of the time we're recording this podcast, CISA had put out a call for information for improving the minimum elements in SBOMs. And I think a number of the recommendations and findings of our work we're seeing reflected in the new guidance that they're given. And I think that regardless of whether they directly used our input or not, we're at least seeing that movement in a positive direction with respect to making SBOMs better, more accurate, more precise, more usable for folks interested in managing and understanding risk in their environments.
Yeah, I mean, one of the most significant reasons we're both here is that working for a federally funded research development center, we can make contributions to the profession, right? I know that recently there was a paper published that captures the lessons learned and the next steps, working with your colleagues here at the SEI. I was wondering if you could highlight maybe one or two things that we've not touched on already that you would want to draw the audience's attention to regarding where we're headed in SBOM, the key challenges yet to be resolved, really sort of what the other work you think that needs to be done.
Yeah, that's a great question. I think there is quite a lot of work yet to be done, and we had some ideas for experiments we would like to run. For instance, one of the variables that we were not able to hold constant is knowing what's in the software package itself. So if we had a software package that we had a ground truth, honest to goodness, golden standard SBOM for, that we could then run the tools against and compare it to reality, we didn't quite have that for the software packages that we were using in our PlugFest because we didn't even know which tool would be accurate in the first place. Right. That was the whole point of the PlugFest, right? But if we design a software package ourselves that we know exactly what's in it and then run the PlugFest again, that's one more variable we could control for and see and compare to an actual ground truth or gold standard. Another element is investigating the dependency structure of SBOMs. I talked about that earlier. Some SBOMs that were produced for the pieces of software that we had the tools apply to, they produced very, very flat SBOMs. Even though the contents were the same, the dependency structures weren't the same. And I'd really like to spend some time investigating that and understanding what additional information we might be able to glean from SBOMs given a more accurate dependency structure. Does risk percolate uphill? How quickly does it percolate? Can you see individual packages that are present across many different elements of software in your ecosystem? Are they almost like the single points of failure in your environment? Can you use the dependency structure to understand how risk flows in your environment? I think there's quite a lot more research that we could do. That's just a couple of ideas.
Right.
I think in our paper,
which is available on the SCI website.
Yes, the paper we published, our blog posts highlight additional areas of future research and additional findings. We had plenty of findings. And also, I did want to highlight that we published our code that we use to analyze the SBOMs as open source software packages.
That's great.
Yeah, huge support to the open source community, and I really want our results to be validated and reproducible to the degree that they can be. So you can find all of those resources on SCINet, like you said. And even though we only used a few very simple Python scripts, they really enabled us to do the analysis, and I'm hoping that they can be helpful for other folks as well.
So I'm hearing there's a great deal of additional experimentation possible. It sounds to me that developers, those that need to think about risk in supply chain, those that build tools that analyze software, that there's many roles in this ecosystem, and that could sort of benefit from increasing the fidelity and the trustworthiness of SBOM. So clearly this is work of high value. A related question, Jessie, artificial intelligence is something we talk about all the time, right? So are there any lessons we're learning looking at traditional computing SBOM that could be applied to artificial intelligence?
I think that's a great question, and I just want to highlight that we can barely get agreement in SBOMs across traditional software, much less very complex AI-enabled systems. I think this is a challenge that we're going to have to tackle, and I know that there is some work in that direction, I think, here at the SCI and at other venues. AI bombs are a thing. Mm-hmm. One thing that I'm a huge proponent of is data strategy and getting data right. Without data, there are no AI and machine learning enabled tools and capabilities. So we've talked about the importance of commit stamping and time stamping pieces of software and being able to map an SBOM and when it was produced to the exact moment that the software was produced. Version controlling data sets and time stamping data sets. Do we need SBOMs for our data sets? Do we need SBOMs or bills of materials for the parameters that go in that inform the decisions and outputs that an AI or machine learning enabled model make? I think there actually are a number of lessons to learn here, and I think if anything, we've learned how difficult it is. Like I said, in traditional software, I think there's just an added layer of complexity here once you introduce AI into the mix, especially when you consider the AI models that are constantly training, constantly updating, are changing, continuously, right? So continuous monitoring of changes of systems in your environment is a challenge ubiquitous across all software.
Yeah, it sounds like if we can focus on some of the foundational elements, it pays benefits in lots of areas. A question, Jessie. So for folks in the audience that are curious about SBOM, maybe not as familiar as you are with the subject, maybe they're like you, maybe they're a mathematician that has a nascent interest in cyber. Where would you suggest they start? So we've mentioned our publications, and those will all be linked to this podcast. But thoughts about other resources or where someone can understand the basics of SBOM? Yeah,
sure. CISA and DHS have a number of resources on their website that folks can go to and read about their work in the SBOM world and in the supply chain world. But also, two of the primary standards and formats of SBOM are CycloneDX and SPDX. Those standards and the folks who really produce and maintain those standards also have a number of resources available for folks who can read all about how these SBOMs are formatted, reasons for including or excluding certain fields and formats, and how they are turned into machine-readable artifacts. So if you're interested in the actual modeling, those are two good places to start. Yeah. In addition to all of the resources we've already mentioned.
Excellent. Well, I have a challenge for both of us. So we both mentioned that we're fans of Formula One racing.
Oh, yeah.
And I think about how many of the cars have software manufacturers' names on them.
Mm-hmm.
There must be a way for us to leverage our interest in SBOM to get into the Formula One world and ask questions.
Oh, 100%. Yeah, I would love nothing more than to have my name plastered on the side of a Formula One car.
Jessie, I'd love to have you back for additional podcasts. I know you have a wide range of interests, and you have so much to offer the audience based on your experience. Thoughts about other topics you'd like to return for to have a discussion like this?
That's a great question. I think it depends on where math takes me next, right? There's a lot of applications of math to cybersecurity, which we've already kind of discussed. For instance, one area that may not be obvious is the application of epidemiological modeling to vulnerability remediation. So you can build models that track the remediation of diseases as people go from susceptible to a disease to infected with a disease to recovered and not sick anymore. Those same concepts actually apply to vulnerabilities and vulnerability management. And I know that there's been some research out there done on this topic, but directly tying that system of differential equations to risk in an environment might be a fruitful area of research that we could address and come back and talk about in the future. It's just another instance of the ubiquity of mathematics and how awesome it is that you can find applications of these little subfields in math to a cybersecurity topic. It really is the marriage of two fantastic areas of research.
I mean, the world runs on math. Right?
It absolutely does.
And I'm always fascinated to meet someone that has the depth of understanding that you do of mathematics.
Oh, well, I appreciate that. It wasn't easy. And I know everyone had a terrible high school algebra experience. I promise that's not normal. And math really is an awesome tool that runs the world. So, yeah, if you're struggling with math, keep trying.
Excellent. Well, that's a great place to end the conversation.
Yeah, of course. Thank you.
Thank you. Well, Jessie, I want to thank you for joining us today. Sincerely, this was an excellent conversation. As mentioned, we'll include links to in the transcript to all the resources you mentioned, including a recent blog post and the technical report written by your team. And finally, a reminder to our audience that our podcasts are available on SoundCloud, Spotify, Apple Podcasts, as well as the SEI's own YouTube channel. If you like what you've seen here today, please give a thumbs up. Thank you for joining us.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, TuneIn Radio, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.